Hi, this is Ying Wu from National Cheng Kung University. The paper I'll present today is Dual Attention Multi-Scale Graph Convolutional Networks for Highway Accident Delay Time Prediction. With the development of science and technology, transportation has become an important part of people. However, transportation has brought us a lot of convenience, but there are also some problems that follow, such as car accidents and traffic jams. For traffic managers, if they can obtain a large amount of traffic information, they may be able to formulate the traffic policy more effectively to alleviate traffic congestion. For drivers, if they obtain road information in advance when go out, they can also avoid traffic peaks as much as possible. Instead of directly predict the congestion level, we focus on predicting the impact and synergies of post-accident congestion on highways. We would like to use accident and highway traffic information to predict the delay time after an accident. What is delay time? When a traffic congestion occurs at a location n kilograms away from the accident, we refer to the time difference between the accident site and the congestion, there as the delay time. This is the overall framework. The framework is divided into two parts, depending on the format of the data. First is the accident status component. Why do we use the entity embedding? When we use one-hot encoding directly when processing categorical data, the transform vector may be quite sparse. In addition, one-hot encoding cannot express the degree of association between categories very well. Entity embedding can map related value closely together in embedding space, revealing the inherent continuity of the data. In the accident status component, first, we distinguish between the categorical and non-categorical data and convert the categorical data into embeddings for subsequent processing. After that, we concatenate both non-categorical variables and converted embeddings. Finally, a self-attention mechanism is used to find the features that it should pay more attention to, which allows the model to effectively capture the relationship between variables. In the traffic network component, we expect to improve the model's prediction results by capturing the relation between road and vehicle conditions. Most of the peer methods use the single GCN to capture the spatial features. However, unlike the urban road network, the national highway is a single route with no intersection, and use only the complete section as a feature may cause the interference when irrelevant points. In addition to using a global graph that incorporates the entire national road stations, we additionally consider a local graph that includes only the station near the accident site. Then, in order to aggregate all nodes vector within the graph, we adopt an NN-based model to extract the latent feature of the graph. Conditions for some roads could be similar. For instance, the adjacent roads may be similar traffic condition in a traffic network. The key idea is to flexibly extract the similarity in the traffic network. The spatial attention mechanism is designed to recognize which parts of the road are more similar and maybe require the model to pay more attention to. Finally, we integrate the result of two information components and then extract the final prediction result by using a full connected layer. We choose national highway number 1 and national highway number 3 in Taiwan as the experimental data, which about 2,000 accidents in total. We divide the information into 3 categories. First category is accident-related information, which contains details of the accident such as the time and the location of the accident. In the second category, we consider some important POI such as police stations and interchanges, and calculate the distance between the POI and the location of the accident. The third category is to obtain the speed and the traffic flow of each station of the national highway at the time of the accident through highway stations. We evaluate the performance of our DMGNet and compare it with the baseline models. In traditional statistical model, the mean and median of historical data are selected as the comparison methods. The performance of the historical median is more robust and relatively stable compared to the historical mean. Among the machine learning methods, tree-based models such as random forest and XGBoost has similar performance, and random forest is slightly better. Since GCN is an essential component of our proposed DMGNet, we also use the basic GCN as a competitive model. The results show that basic GCN indeed perform better than other baseline expected for DMGNet. Finally, the table also shows that the proposed DMGNet outperform other methods in all evaluation metrics. To verify the effectiveness of each component of DMGNet, we design experiments to evaluate the prediction results of different component combinations. We then briefly introduce each of the following components. First, EN represent the entity embedding are used to processing the categorical data, and CA represent the context attention. Find out which feature they should pay more attention to. And the MG represent the multi-scale GCN, which is used to obtain the special latent feature in the data. And the SA represent the special attention mechanism. According to the figure on the right, we observe that adding EN or CA is slightly better than using the DNN. However, when it comes to the overall model improvement, MG is the most important one, given the significant decrease of both evaluation metrics. Here, we verify the impact of various types of feature combination on the model. The following are some of the features we have defined. T denotes the time, and P denotes position, W denotes weather, S denotes traffic sign, RS denotes road state, L denotes the type of the land facilities. PR denotes the personal related feature. DP denotes the distance to the nearest POI. Because the PR is the most relevant factor in the accident, we include it in every combination. First, we use the basic feature T, W, and P, and found that the results were similar. After adding road-related features such as RS and L, the results were improved greatly. It is worth mentioning the feature DP, which is the distance from the nearest POI to the accident site, has an obvious impact on the result. Finally, we determine the number of stations in the local graph through experiment, hoping to obtain the most appropriate local area information. When the local graph is constructed, we find the number of L stations located in the front and back of the incident. From the table, we can see that when N is equal to 1 or 2, L is equal to 15, will have the most ideal result. However, the results are slightly different when n is equal to 3. The performance is better when the L is smaller, just like L equals to 5 or 10. In this work, we contrast to previous research approaches. We aim to accurately predict the delay time of road behind the congestion caused by a vehicle accident. We propose DMGNet, which integrates a dual attention mechanism and a multi-scale consideration of road network information to effectively predict the delay time of traffic congestion. Experiments conducted on traffic flow and accident information of national highway in Taiwan prove the applicability and robustness of our model on this task. And for the future work, we can add more external features to further improve the accuracy of prediction. And we can analyze the impact of various environmental factors on the accident delay time. Finally, we can cooperate with traffic authority so as to achieve more efficient control and improve the quality of the driving. This is my report. Thanks for your listening. If you have any question, you can contact me with the below email. Thanks.